The next application of kinematics is in the problem of relative motion. So far, everything we've discussed about moving objects assumes that we are observing them from a fixed point of view. That is, we are standing still. But how would an object appear to move if we, the observer, are also moving? We begin with a very simple scenario. Suppose there are two cars moving along a straight road. Car A is moving at 10 meters per second and car B is moving at 12 meters per second. Car B is in front of A and clearly B is moving faster. As usual, we take the right direction as positive and the left direction as negative. We can deduce that for a person inside car A, they will see car B moving away at positive 2 meters per second. For a person inside car B, A is receding away at negative 2 meters per second. Clearly, the velocity observed is the difference of the two individual velocities. From here, we can define a quantity for velocity of B as observed from A, VBA, as being equals to VB minus VA. Similarly, velocity of A as observed from B, VAB, is equals to VA minus VB. Obviously, VBA is equal to the negative of. Now let us see how we use Hooke's law with an example. Consider a block of mass m suspended from a spring of constant k. This block sits on a slope of angle alpha. If the block is in equilibrium, what is the spring extension x in terms of mk and alpha? As usual, let us draw the free body diagram. We have the weight mg, normal force perpendicular to the surface, and now a spring that is pulling on the block, preventing it from sliding down. From Hooke's law, the magnitude of the force is kx. Resolving the weight along the direction of the slope, we have mg cosine alpha. Accordingly, perpendicular to the slope would be mg sine alpha, though we will not be using this at the moment. The box is in equilibrium. Therefore, Newton's law says that the net force along the slope must be 0, which is to say that mg cos alpha is balanced out by kx, and these two magnitudes are equal. Solving this for x, we have mg over k times cosine alpha. The next force we will talk about is friction. There are two kinds of friction, which are called static friction and kinetic friction. Friction occurs between an object and some kind of rough surface. As the name implies, static friction occurs when there is no relative motion between the object and the surface, so they are just touching each other without moving. On the other hand, kinetic friction happens when an object is moving against the surface. This is like rubbing, scraping, or sliding over a surface. Let us talk about static friction first. And we first assume for now that the object in question is having zero acceleration. This force is, the frictional force is responsive and it reacts automatically to what is happening to it. So suppose we are trying to push a box that is sitting on a surface with friction. Before we touch the box's free body diagram has just two vertical forces, weight and normal force, as we expect. But when we apply a force F horizontally towards the right, we realize that the box doesn't move. Everyday life calls this friction, but in the language of Newton's laws, we say that there must be some other force that is cancelling my force F. And let us call this force Fs. So in the horizontal direction, the net force is F minus Fs. Newton's law says that this should be equals to ma, but we know that the acceleration is 0, so the right hand side of the equation is 0. And we arrive at the conclusion that the frictional static friction force Fs is exactly equals to F. Of course, static friction cannot resist very strong forces. If we increase our pushing force F, we know that at some point the friction will eventually buckle and the mass will finally move against the surface. So the static friction can only resist up to some maximum point. And if we push up to some maximum value, Fmax, the static friction will finally fail. This value will be equal to a constant mu s times the normal force. This mu s is called the coefficient of static friction, and its value depends on the surface. Therefore, the possible magnitudes of Fs lies between the range of 0 and mu s times n, depending on the value of the exerted force F. Now, what if the object is having non-zero acceleration? Suppose the box is sitting on the back of a lorry that is accelerating. Obviously, static friction can exist as long as the box doesn't slide around the surface of the lorry. Static friction is when the object doesn't rub against the surface, and this remains true when the lorry and box is moving at some value of acceleration. As long as they both share the same acceleration, there is no relative motion between the two of them. The vertical forces are still the same. We still have the normal force balancing out the weight mg. And if some external force F is exerted on the box, the static friction will attempt to counter this with a force Fs. So in the horizontal direction, the net force is still F net equals to F minus Fs. But now this equation is not zero. We have to remember Newton's laws. F net is equals to mass times acceleration, and the acceleration is not zero here. Solving this for F, we get Fs plus ma. So now, what is our applied force F that will finally slide the box over the surface? We need to exceed the maximum static friction. As before, the maximum case is obtained by substituting Fs with mu s times n. So the Fmax required is equals to mu sn plus ma. We conclude that the acceleration of the system affects the force Fmax required to push the box across the surface. And of course, when a is equal to 0, we just go back to the same result as our previous case. Kinetic friction is much easier to understand compared to static friction. It occurs when an object is moving against the surface. Unlike static friction, the magnitude of kinetic friction is fixed. So if we call static friction as Fk, it will be equals to mu k times the normal force. The direction of kinetic friction is also fixed. It is always opposite the direction of motion of the object.